So you probably, unless you're a hermit, know that we have actually detected around other stars, we have detected planets orbiting other stars. And don't feel bad if you didn't know that, but we definitely have. Two ways that we generally can know that there are stars that have what we call star systems, so stars that have planets in orbit about them. One is to directly see that planet. Now, that's a tough thing for a couple of reasons. Well, for many reasons. One is that stars are way far away from us, and so by the time you get an object way far away from us and you're trying to look for a tiny planet, it's hard to see. And remember, planets aren't creating their own energy, so the only reason we see a planet would be because it's reflecting light from the star it's orbiting. And then the other thing is that radiation from the star itself kind of washes out our ability to kind of see close to the star. So directly detecting or seeing a planet in orbit about another star is kind of a tricky thing. So more than likely I'm going to discuss a couple of different ways to indirectly detect or to kind of infer that there is a planet in orbit about that star. And first off, I'm going to consider our own solar system. The largest planet in our solar system is Jupiter. And actually, Jupiter is relatively large, and because of its size, it and the sun kind of play a dance around a common center of mass. Okay, so I don't know if you can see this, but here's the sun and here's Jupiter. Okay, and then Jupiter ends up down here and the sun's right here. So the common center of mass is kind of where that dot is for Jupiter. Okay, I don't know if you remember, there was actually a planet-moon system recently when I introduced Pluto. Pluto has a large moon and actually has 3 other moons, so it has a total of 4 that we know for sure. But one of Pluto's moons, Charon, is so large that Charon doesn't orbit its planet Pluto, its dwarf planet Pluto. Actually, both Pluto and Charon orbit a common center of mass, kind of like this. So if we were on a distant star, or I should say if we were on a planet associated with a distant star, we could actually kind of see the sun kind of wiggling, back and forth. And that would be because it has another body, in this case a planet, in orbit about it. So there you go. So this would be an indirect method. We would indirectly infer that there is a planet in orbit about that star because we see the star wiggle. Okay, so kind of sticking with the wiggle of the Earth, the wiggle of the sun around a common center of mass. We can actually then deduce, we can get to masses by understanding the wiggle. Well, another way we can indirectly tell that there's a planet uses the Doppler effect. And do you remember that we said that the way the Doppler effect works is if an object is coming towards us, you'll see a blue shift, and if an object is going away from us, you'll see a red shift. Okay, and actually this goes again back to the point that the star is wiggling. The star is actually wiggling, orbiting a common center of mass, as is the planet that we can't see. And so we see, as long as this is proper motion, okay, directly towards us and directly away from us, we can actually see, radial. As long as this is radial motion directly towards us and directly away from us, we'd see a blue shift and a red shift, blue shift and a red shift, alternating. Even if we couldn't see a wiggle, we can detect it using Doppler. Okay, does that make sense? So again, looking at the wiggle in a distant star, and it's actually wiggling or moving around a common center of mass because of a large body, a planet we can't see. So the first planet in orbit about another star was found in Pegasus, the constellation Pegasus, 51 Pegasi, and the planet has a 4-day orbital period. Isn't that crazy? Here in a minute we're going to see these extrasolar, or I have the term extrasolar planets here. Oftentimes they're just simply called exoplanets, and I think I use that later. Exoplanets and extrasolar planets are the same thing. So these exoplanets or extrasolar planets generally are pretty darn close to their star. And so one of the Keplers laws said that the closer a star is to the sun, or I'm sorry, the closer a planet is to the sun or a star, the faster it'll move. And this one has a 4-day orbital period. Isn't that crazy? Okay. So another way that we can indirectly know that there's a planet there is if that planet from our line of sight passes in front of the star, it will eclipse or steal a little bit of light. Okay, we call it a transit when the planet, we call it a transit when a planet goes, actually when anything goes in front of anything else, because but in this case, we're calling it a transit when the when the planet is going in front of the star. As the planet orbits the star, it's going to go in front of it. And if it's in our line of sight, we can catch that. So what will happen then is we will see the stars, the light coming from the star will dim a little bit. And we'll know that the planet is passing in front of it. And we can indirectly know that there's a planet. So for instance, this is a light curve. So here we see the full light of the star. This is where some of the starlight is eclipsed, and because of the planet passing in front of it, and here the planet has completed its pass, and we get the full light from the star again. So again, here's another light curve over here. If you compare these two light curves, actually for the second one, B, can you see where it's how do I say, less light is eclipsed, and so the size of that planet must be smaller. Oh, wait a minute. Darn it. Now I'm reading this. This actually is the same system. And what they're showing here is that as the star, darn it, as the planet passes behind the star, we also see just a little bit less light because the planet was giving us some light too. Final answer. Okay, so it has to be in the direct line of sight in order for this to work for us. That's kind of limited. So direct detection, not impossible. So what you're looking at here is the star is blocked out, starlight's blocked out, and we must be looking kind of face on to this star system, and the arrows are showing you the planets. So it's pretty cool. Okay, so extrasolar planets are the same thing as exoplanets. So just to kind of compare what sort of planets are we seeing out there? Well, when we compare planets, especially to the 8 planets in our solar system, we might kind of think of how long it takes those planets to orbit a star. We might think of how far are those planets from the star as they orbit the star, and then we might think of the shapes of the orbits. Remember that there's this that planets will orbit stars in shapes called ellipses, and there's a degree of eccentricity about how oval or circular that elliptical shape is. Another thing we might compare planets out there, exoplanets, is how massive is the planet, what sort of size, what sort of density. Does it look like a Jovian or terrestrial planet? Its composition. So I'm going to take you just briefly to one of NASA's sites here. Now, I think I've mentioned before in lecture, but there is a telescope, the Kepler Space Telescope, and it is designed just to look for planets in orbit about distant stars. I recently went to this website, and I tell you, NASA has the best websites. I'm just going to kind of let you check it out yourself, but if you're interested in exoplanets, this is your site. So, for instance, you might recognize this is Cygnus, okay, Cygnus the Swan or the Northern Cross, and then over here is actually, these are, I believe they're individual stars that have planets in orbit about them. I don't know, I'd have to double check. But here's just all sorts of things for you to look at. Okay, so extrasolar planets or exoplanets. Most of them are closer in than Jupiter. Okay, the ones, and it could be that there are more distant planets in orbit about the distant stars, but they're harder to detect. So this is a very busy figure from your textbook. Now notice each dot represents an extrasolar planet, and along the x-axis down here we have its average distance from its star, and it's in astronomical units. So 1 astronomical unit, this is where the Earth is. Okay, the Earth is from the Sun. So all of these would be closer than the Earth to their star. And you can kind of see where Jupiter is. I believe that's a green dot. I think our solar system are marked with green dots as planets. The other thing it has is the orbital eccentricity. So down here you can see that our eccentricity is, we're pretty circular. And notice that the eccentricity increases, up here. I mean, that's pretty darn eccentric, which means it's more oval. So we have that information. The other important piece of information is relative size. So the size of the dot, there's like 4 sizes of dots here. And here's the key. So the smallest dot is less than 0.1 times the mass of Jupiter. The second to smallest dot is between 0.1 and 1 times the mass of Jupiter. And then we get 1 times the mass of Jupiter to 10 times the mass of Jupiter. And the big dots, look at this, I mean, these are some big dots, are actually more massive than 10 times the mass of Jupiter. So there's a lot here, but, and I believe the published date for this text was 2011, and so maybe a lot has happened since then. So generally speaking, with regard to mass, most planets are more massive than Jupiter. Okay, if Jupiter's right here, one of Jupiter's masses, we can see that most planets are more massive than Jupiter. I don't know what else to necessarily add to that. So looking for planets to date. So it's kind of tedious. We mostly see planets indirectly by indirect methods, and we're seeing that most stars have planets in orbit about them. So extrasolar planets, remember, are the same thing as exoplanets. It's a fascinating field of